Cool. Okay. Well, again, everyone, welcome to this first virtual session of Paper Club. Today, we're going to be speaking about a paper about uncertainty estimation using ensembling in deep learning. I want to share my overall impression of the paper first. So my overall impression is that the paper lacks a bit of a punch. They make a bunch of somewhat controversial claims, which we'll go through in a moment. And I don't think that they provide enough information to support those claims. But in any case, the paper is still interesting because it shines some light on an area of machine learning that is often overlooked, which is uncertainty estimation. We have covered some of the papers that they talk about here. If I just happen to skip over something and you have a question, just ask about it, and more than happy to answer the question. So yeah, let's start with the paper, and I think it's good to speak about the motivation behind this paper. So the main motivation behind the paper is that deep neural networks, as we have possibly discussed in great lengths, they do not provide reliable probability estimates. So they are typically overconfident, which means that they can have very high accuracies, but they are completely rubbish at estimating actual probabilities, the actual probabilities of occurrence in the data. So this is a big issue if you're interested in, for example, measuring uncertainty. Uncertainty relies almost exclusively on having a reliable estimate of the probability distribution of the data. And for example, if you want to measure uncertainty as the standard deviation, you cannot do it if your machine learning method is overconfident, because it will always say that it is very certain, even if it's wrong. So this has two very specific applications, which, well, we happen to be very interested at NPlan, but we think that it is something interesting for the whole machine learning community as well, which is, one is out of domain uncertainty estimation, which means how do you know if the data that you're looking at does not come from the same probability distribution as the data that your classifier trained on. And then there is the out of sample or in domain uncertainty estimation, which means that the classifier has seen these data points in the past, but it is not certain about what prediction it should give. So they are two different things, and typically the behavior that we want is out of domain estimation. We want the classifier to be very uncertain about the predictions, so we can quickly identify them as out of distribution. But out of sample, we still want the classifier to be uncertain, but we don't want it to be completely uncertain. So we don't want a completely uniform probability distribution. We want something a bit more flat. So imagine that something has a temperature scaling on it, but we don't want it to be overconfident. So we don't want it to be too confident just because it is in domain, if that makes sense. So in that sense, those are two different areas of research, and so this paper is mainly concerned with in-domain uncertainty estimation. They leave the out-of-domain for other works, but I think that many of the techniques that they show here could actually be also applied for out-of-domain estimation. So let me see if I can get the spotlight. Okay, so the paper, they try to make three main contributions. The first one is they try to show that the metrics that are typically used in machine learning, that many of the metrics that are typically used in machine learning to estimate the uncertainty of a classifier are not actually good, either because they are biased or because they depend on certain hyperparameters. So we'll see the reasons that they give. Well, we'll get more into it when we get to that section, but in general, they are very rational, like they're very rational explanations, but they don't give that much data to support their claims. The second part is the pitfalls. So they try to show the pitfalls of ensembles. So ideally, if you think of an ensemble, they claim that one of the ways to see an ensemble is just a collection of different different methods that ideally can settle at different points of the loss landscape, and then you can have better estimates of uncertainty because you can see different ensembling methods. And they claim that if an ensemble method can give you different points of the different local minima of the loss landscape, then they are better. This is a bit controversial because, of course, there's a lot of theory on ensembles, and well, we can see later what is their rationale for this particular purpose of in-domain uncertainty estimation. They seem to give some good intuition of why those ensembles that can actually converge to different points of the loss landscape are better. And the last point is that they say that there's a test time data augmentation missing in ensembling, that we typically try to use just the output of the ensembles as a good estimation for uncertainty, but that test time data augmentation is can actually give a lot better estimates of uncertainty. So they make a bunch of disclaimers of what they are not doing in the paper, which I guess, in my opinion, it gives them some credit, because they're not making generalistic claims, but rather they're trying to say, well, we explored this particular site. But some of these claims are very they seem very strong. So the first one is, of course, they are only exploring in-domain uncertainty, which fair enough, that's fine. But there's another claim that they only consider clean data. So they're looking at data that is clean and then it has been augmented. So that is a bit of a big claim, because typically you would not find clean data out in the world. But anyway, it's still a good way to show how these methods work and how you can compare different things, taking away the, call it, aleatoric uncertainty that you can find in the data. And this last bit is probably one of the most controversial ones that I read in the paper, which is that they left out many techniques that are used to either speed up the training of ensembles, or improve, or make them more compact, or make them faster to use at test time, which is a big claim, because afterwards they say that, well, but deep ensembles are better because they have less members and they're easier to deploy. So yeah, but you did not explore acceleration procedures. So I guess that those are the disclaimers of the paper. But I mean, within this scope, I'm willing to say that, okay, that the study has some validity. So let's go to the first point. The first point is, well, what are the current pitfalls of the metrics that are used for uncertainty estimation? So they start with the tested log likelihood, and they say that, well, this is a very common metric, and it can be used to measure the calibration of the classifier at test time. But they argue that it is very sensitive to the softmax temperature, which is true. So if you can make the loss smaller simply by increasing the softmax temperature or reducing the softmax temperature. So depending on how bad your classifier is, you can decrease the loss by either making your classifier more confident or less confident. So that's fine, and it's probably true. So what they argue is that the log likelihood comparison is only relevant at the optimal temperature. So they say you find the optimal temperature for your classification ensemble or for whatever model you're using, and then you compare the log likelihood at the optimal temperature, which seems fine. For some reason, they explain it later on, but basically they call that the calibrated log likelihood. So once you find the optimal temperature, you find the optimal temperature, and then you measure the log likelihood in the test data, and then you have the calibrated log likelihood. But we can see the formula when we get there. And they say that it is equivalent for the Breyer score. So they say that they are very highly correlated. So that's fine. So they say they don't use Breyer score just because it's the same as the calibrated negative log likelihood. But one interesting property that this calibrated log likelihood has is that it has a very strong correlation with accuracy. And the reason we would like that, it's because at test time, we do not have the ground truths. We don't have the labels. So we would like a metric that sort of serves as a proxy for accuracy. So if there is a strong correlation between the calibrated log likelihood and the accuracy, then that means it's actually a very good metric to measure both calibration and test and generalization accuracy. The second set of metrics that they discard are the area under the rock curves and the precision recall curves. It's very simply because they so they are they're very biased depending on which model you choose and on the hyperparameters of the model. So it is not a fair comparison across different models. So well, they say that basically a model can have good precision and poor recall, and that may be okay for that application, but maybe another model should have high recall, low precision, and then the area under the curves do not allow you to compare different models. As a counter proposal, they say to use the rejection confidence curves, which it's basically that you also measure the area under the curve, but on one axis you will have the number of examples rejected, and on the other axis you will have the so the accuracy of the model after rejecting all those examples. So that does help you compare different models, because you say, well, you want to compare at this number of rejections, and then what's the accuracy when you have rejected 10, 20, 1,000, a million samples. Cool. I realized that it is a lot harder to go through a paper when you can't just ask people how they're doing. Anyway, let's carry on. If anyone wants to say something, again, just raise your hand, and we're more than happy to have more people in the conversation. Cool. So the last thing they talk about are the calibration metrics. Now, the expected calibration error we have spoken about before. It basically measures the difference between the confidence of your model, so the softmax output for the correct class, and the accuracy at that point. So the accuracy for that class, or for those predictions. And ideally, you want that if the model has low accuracy, you also have it to have low confidence, and if it has high accuracy, you want it to have high confidence for that classification as well. So well, the clear problem with this is that it only takes into account the argmax. So of course it's heavily biased towards a model that makes highly accurate predictions, but then so yeah, it's biased towards the argmax. Ideally, you want something that makes good predictions across all the classes that you are classifying. So that is this thresholded adaptive calibration error, which is, it's actually not very interesting. It applies a threshold to choose which softmax activations you're going to use, and then it uses an adaptive binning to calculate the edges of the bins, and then you have an expected calibration error, but with adaptive bins. They do say it has some biases, but it is less sensitive to the parameters than the expected calibration error. So they argue that this is a better metric, but they still don't use it later on. So I'm not really sure why they make this whole explanation. And finally, the calibrated log likelihood, which is the one mentioned at the beginning. They basically do a test time cross validation to find this metric. And what they do is they optimize the log likelihood for half of the test set. So they want as low possible log likelihood, and then they measure the log likelihood on the other half. And they repeat that several times so that you get an error bar around it. And this is the metric that they will use to compare all their approaches. Okay, does that, well, yeah, I was going to ask if that makes sense. By show of hands, does that make sense? Are people there? Ah, there you go. Cool, it's good to know that people are here. Thank you. Okay, so this is the whole first part of the paper, and well, they're very rational explanations, but again, there's not much juice behind it. They just make a very long explanation of why they're going to use this calibrated log likelihood and that test time cross validation. So I guess it's fine. It's very thorough, but it makes for some heavy reading, which is in the end is not very needed. But that's fine. Everyone can do their paper as they want, I guess. So then they go on a long explanation of which ensemble methods they're going to use, which we don't need to get into very much. But what is interesting is how they do. So how they do data test time data augmentation. And well, all these formulas just to say that you pick your transformations, which in this case is a horizontal flip or a vertical flip or a random crop. And then you define a probability of picking one of those alteration methods for the images. And ideally, you would run a prediction over each of your randomly picked augmentation methods, and then you average over all the predictions. So that's what it's doing here. And they argue, well, that is going to give you your closest distribution to the real data. So basically, you're assuming that there's going to be noise. So we have a question. What's the full Nixon 2019 reference? Full Nixon 2019 reference. Where is Nixon 2019? I'm not sure I see. Where is this Nixon 2019 reference? Can you say in the chat? So, interesting. Yeah, well, maybe it's this one, Jamie Nixon, Measuring Calibration in Deep Learning. Cool. Okay. Okay, well, okay. Spoiler alert, spoiler alert. Okay, so yeah, so all this fancy work just to say you pick a number of random data augmentations, which is just a bit of data corruption. And then you average your predictions over them, and that gives you the data augmented prediction. It is funny because in the experiments, as we will see, they make k equal 1. So they make one random augmentation, and they use that as a generalizing data augmentation technique. Is this some about dropout instances? Yes. So yes, if your data augmentation is to use dropout, but I think that so this particular one is about the data augmentation. The dropout instances is going to come further down in the choice of ensembles. So for instance, if you're using a dropout based ensemble, this L would be the number of your dropout. Done. Okay. Yeah. Yeah. In this area, we consider the following ensembling technique. All these techniques can be summarized. Yeah. Okay. Oh, wait. No, yeah, you're right. Arvid is right. So this particular formula refers to the ensembling techniques. So K would be your number of ensembles. Okay, sorry about that. So yes, if you're using dropout, K would be your number of dropout forward passes. If you're using an ensemble of deep networks, then this would be your number of members in the ensemble, and so on and so on. Okay, cool. Sorry about that one. And yeah, and then And then comes the data augmentation, which is, yes, you can sample from the corresponding data augmentation strategies to have different versions of the same example, which they then make one. And here is where they talk about the test time budget. So they say that, well, this particular formula, it depends on, so how many forward passes you do is going to affect your test time budget, which they take into account later. But, well, you said at the beginning that you're not exploring methods for accelerating your ensembles. So that one's a bit flimsy for me. Okay, so the first experiment that they do is to show how many of these, so they're trying to show how many of these ensembling methods, they're very good, but they all fall short of a very simple ensembling mechanism, which is a deep ensemble. A deep ensemble is take as many deep networks as you want, give each one of them a random initialization, and then train them all until they converge. What that gives you is you have several local minima of the loss landscape. And what they would like to argue is that those are the best possible ensembles when you're trying to generate probability distributions. They use this calibrated log likelihood as a measure, and then they speak of the deep ensemble equivalent. So because they are trying to compare the different ensembling methods, what they are trying to say is, well, they all depend on their own hyperparameters and they all need to be individually optimized. So it is not always trivial to compare different ensemble methods. So what they say is, okay, let's find a deep ensemble that can replicate the performance of whatever ensemble method. And then you repeat that for all the ensemble methods that you want to compare, which are dropout, FGE, KFA, C Laplace, SSE, and so on. And then they say, well, let's see how many members do we need in our deep ensemble to replicate the performance of the original method that we're trying to assess. And they produce these plots, which, as they show, first they say that, so this is deep ensemble compared with deep ensemble. So that is a slope 1 line or close to 1. And they say that all the methods can fall into 2 categories. So first, they all fall short of the deep ensemble. So they argue that deep ensembles are actually the best possible ensemble method that you can think of, which is controversial because it is the best one in the sense of the calibrated log likelihood, but that doesn't mean that they are the best ones altogether. But anyway, after that, okay, question, is it obvious that deep ensembles are as expressive as any other method, or is it because it is image data? That's a very good question. Arvid, maybe you want to expand a bit on that? So hello. Arvid, you're on mute. Oh, do you not have a microphone?
Oh, wait, can you hear me?
Yes, we can hear you now.
Brilliant. No, I was thinking that obviously a deep ensemble doesn't tell you necessarily how deep it is and what are the parameters. So you would expect that there's a limit to how expressive a particular network can be. And so why would an ensemble be, how to say, even more expressive, right? Say if you have an ensemble of other trees, might be able to have a more diverse view of the data, which might be not true for image data, because image data is kind of special, right? Where you would expect that deep networks might outperform other methods, but not in general, no?
Yeah, that's true, and that's probably one of the main faults of this paper is that they are so they only look at image data, and I think that they're not properly addressing those limitations of whether all these methods that they're looking at, all these ensembling methods that they're looking at, are actually optimized for image data. They do mention at some point that they are using convolutional architectures for all the ensembling methods. But yeah, it's that is true. Maybe if you used one of these methods with a different architecture, then it would become better.
Cheers.
Cool, no worries. Okay, cool. So yeah, so just to carry on with this plot, they say that all these, they fall in, so that makes them fall into two different categories. One category are all those that have a linear, a linear trajectory, so to speak. And they say these are the methods that are capable of converging to different local minima of the loss landscape. And they say that those are the best for to test in-domain uncertainty because they give better probability estimates, which in the end means that they are closer to a deep ensemble. And all these that plateau are all those that are not, that always converge to one local minimum of the local, of the loss landscape. So, well, the whole argument is to say that deep ensembles are probably one of the best possible options because they're easy to implement, quote unquote, and they give very good estimates of probabilities. Okay, and the other experiment, which is rather interesting, I would say, is the test time data augmentation experiment. And so they show here the different augmentations that you can do on an image. So this is a random crop. That one is a horizontal flip, and that one, sorry, this is a horizontal flip, and this one I think is a vertical flip. Well, anyway, they define their data augmentations, and then they sample one of the data augmentations in the test set to do this calibrated loss. And they see what are the results on the other half of the test set. And what they show is that basically, given enough members in the ensemble, using data augmentation is going to help them have better accuracy, so lower error, and also lower calibrated log likelihood. So that goes in line to the last thing that they were saying, which is that, well, the test time data augmentation is necessary in ensembles, even if it's not used consistently. And it also goes to show that the deep ensemble well, outperforms every other method in this particular accuracy metric. And that is the last point that they want to do. They make a list of their main contributions. Like I said at the beginning, my personal view of this paper is that it presents some interesting results, but they make some claims that don't necessarily generalize to a real life scenario. So, for example, they speak about how up here they speak about how using a part of the training set as validation is not as good because then you have the public test set, which, well, that's very nice for public challenges, but when you're out there in real life, who cares? You can divide all your data however you want. There's no train and test set per se. And they make a bunch of claims that, again, may be true for images, but may not necessarily be true for on a more general sense. So overall, an interesting paper, I think. Can we hear the opinion of other people? Anyone wants to speak? Raise their hand. Fahan, Joao?
I found the paper very interesting.
Yeah, it's very interesting.
Very nice, very nice. Okay. So does anyone have any more questions about the paper? Something that they would like to know in more detail? Interesting, thank you. As for reliable benchmarks, what would they be? Okay, so we have a question that says, a large number of unreliable metrics inhibits fair comparisons of different methods. Because of this, we urge the community to aim for more reliable benchmarks in the number of setups of uncertainty estimation. So this last sentence, it's related a bit to the beginning of the paper. So uncertainty estimation in machine learning and deep learning in particular has sort of fallen under the radar because, well, last time we spoke about this, I called it the greed for accuracy. So we only care about models giving good accuracy metrics. And this uncertainty estimation part has fallen under the radar. So in every paper addressing deep learning uncertainty, you will see that they're jumping through hoops trying to define what is a good benchmark for uncertainty. So what they're calling for here is, well, can there be a labeled data set specifically for uncertainty? So at the moment there is none, or none that I know of. If someone knows of one, please let us know. And so I guess this is sort of the spirit of this last sentence. So if you go in detail on the paper, you will also see that, well, here they're trying to measure uncertainty, but they have to make their own metric and then sort of justify why their metric is general enough and why this is a good measurement for uncertainty. So I guess what they're asking for is more studies like this one. I hope that answers your question. Cool. Any more questions? Okay. So thanks everyone for coming to this first virtual session of Paper Club. We have a healthy amount of attendees, which is encouraging. So we'll try to follow the same, maybe I can stop sharing for this. Okay, no, not stop sharing, stop recording.